Hello, my name is Josh Kakade. I'm a junior at the Dayton Regional STEM School, and this year for Science Fair, I made an autonomous lawnmower. So this is what it looks like. It's very cool. As you see, the custom 3D printed wheels on there, and a custom 3D printed blade that's actually safer than the standard blade currently equipped on normal lawnmowers. So we'll talk about the history of lawnmowers very quickly. Here we have the real lawnmower. No mechanical portions at all. It's all fully mechanical, no electrical portions at all. We have the push mower, and then we have the riding lawnmower used for bigger applications and bigger yards. Okay, here's some statistics about lawn mowing. The global lawnmower market size was valued at 26.2 billion in 2020, and it's projected to reach 53.7 billion in 2030. U.S. households spent 15.9 billion on lawn care and gardening services in 2015. Autonomous lawnmowers cost $900 to $20,000. Mine can be made for $300. Lawnmowers cause 90 deaths annually and 85,000 injuries annually. 800 children are run over each year by lawnmowers, resulting in 600 annual amputations. This is something that no child should ever go through, and mine actually prevents that from ever happening. A new push mower costs on average $300, while some riding mowers cost up to $5,000. According to a study published in 2018 by Johns Hopkins University, injuries from lawnmowers send close to 6,400 people to emergency rooms every year, and there are about 16 blades of grass in the world. That's 14 zeros. Alright, so here's some autonomous lawnmowers currently on the market. We have one for $1,100. Move my camera here. We have one for $1,800. We have this one down here, $4,100. We have this last one down here for $3,000, and the Pro version for $3,700. So here is my prototype. So this is what I made in October of this year of 2021, and this is my initial prototype for my final lawnmower, for my final autonomous lawnmower. Here's another picture. Here's a mechanical system behind it. Here's it actually cutting the grass, and here's a giant blade that causes many injuries amongst kids and adults too. So here's actually it moving, running around. So the problems are: it's big, it's clunky, it's heavy, it lacks intelligence, it's costly, and it's unreliable. These motors on here are very expensive. They're meant for wheelchairs that carry 300 pounds, and yeah. So I made my lawnmower using these components. First off, we have our custom chassis. I designed it initially with cardboard, and then I sketched it up like this. Here we have 16 inches on either horizontal side or vertical side, and then 10 inches horizontally. And we have that 4 times, 1, 2, 3, 4, and that makes a total of all the aluminum frame, a total of 72 inches, 16, 16, 32, then 32, 42, 52, 62, 72 inches. So I made it up with cardboard. We have our battery here, and then we have our 2 motors all marked with cardboard, so I can figure out where everything goes really fast and really easily. Here's our chassis again. This is somewhat final, and here's what it looks like in the current state. When the chassis is very strong. I can stand on it and it won't break or bend at all. I could probably throw it across the street and it wouldn't break. So here's the RC transmitter and receiver. So this is used to, this is a transmitter and it talks with the receiver, and this is how I communicate in RC control, obviously. But no one likes RC control when you have autonomous mode. So here is autonomous mode. It uses a microcontroller, and the specific microcontroller, the Raspberry Pi. Okay, you see it? Yeah, it's cool. So the Raspberry Pi basically talks to this little guy here called the motor controller, and the motor controller tells the motor what to do. The reason you can't plug the motor directly into the Raspberry Pi is this motor needs 12 volts of electricity, and the Raspberry Pi would get completely fried if it had that much volts of electricity going through it. So the motor controller acts as a middleman, inputting the signal from the Raspberry Pi and telling the motors how to act upon that signal. So here's a picture of the motor controller here, and yeah. So 3 printed parts. So we made custom wheels for this. Okay. I originally wanted these to be printed in pink, but for breast cancer awareness, but that was not possible as they didn't have pink filament. But here you can see the wheels. We have this tread like wheels here, and then we have around here, and then here's a side view of it. So here's, I'll just make my camera quickly. So you see the wheels right here, pretty cool. This goes on the motor shaft with a little keyhole, you see me through it, and we have the treads here. This is important to note that these treads are very different from the final treads, these being conical, and well, these are like more grippy into the ground. So next slide. So here's actually it in CAD. As you can see, it's very messy. That's also something I improved on. Okay, so here's some more pictures of the wheels. These are the same wheels that are on the lawnmower right here. And if we go to the next slide. So here's my final draft of the wheel right here, also in pink for breast cancer awareness. But it was printed red as they didn't have pink filament, of course. So here we go. We have cones right here that I actually mathematically calculated the height of it using laws like sines and cosines to figure that out. And yeah, so there's some partial trigonometry involved with that. So here's the side view of it right here, and here's what it looks like from the front. So you might be asking, why did I change from this design with the treads like this to a more conical design? So this design, it didn't grip onto the grass as well as I'd like it to, and it was less efficient than this. This conical design is way more efficient. It can be seen in professional football cleats, as they have those little spikes, not spikes, but the spikes almost that grip onto the ground, and they allow the player, the athlete, to have as much movement as possible. So that's what it looks like on the robot. And so here's the original design versus the final design. As you see, there's treads right here compared to the final treads right here. So our next part is the custom blade. So this is where the biggest safety method is made compared to the standard blade, which is very dangerous. It can actually amputate people's limbs off, and that's not good. So I made my own custom design inspired by similar autonomous lawnmowers out there. So we have, it's a two-part system. That's the bottom, of course, that you're seeing on screen. And then if we take this top part off, oops, excuse me. So we have this flat portion that goes onto the lawnmower or blade like this. Okay, and boom. But what actually cuts the lawn? So here we go. Here's our single edge razor blade right here, but it's a sticky note. But basically, you would drill a hole through a blade right here, around 3/4 of the way into it, and you would put them inside here, as so. Okay, and boom, it's inside there. So what's the point of this? So when it's spinning really, really fast, the blade comes out because of centrifugal force, right? And it cuts the lawn. But when the blade comes to hit something, for example, your hand, you see this blade's about to hit my finger, but it will go retract inside. This will still hurt you, but it will drastically lessen the effect of the cut on your hand. So here's the top portion, as I mentioned earlier. So this is around 6 inches in diameter, and that gives it around a 7 inch with the blade sticking out, protruding out a little bit, a 7 inch cut radius. So here's it being assembled. And so for programming, so how did I program all of this? So we have our chassis, we have our wheels, and we have our components already there. So how do I program this? So first, our first sensor, probably the most important sensor on here, is the gyro sensor, or second most important actually, the gyro sensor. So here's a little video of it playing. So wait, before I play the video, the gyro sensor, what it does is it detects the angles of pitch, yaw, and roll. Okay, so on a plane, pitch is the vertical, yaw is the left and right, and roll is obviously that other dimension. We just roll like this. Okay, so the gyro sensor, the reason I'm using this is when you tell the robot to drive in a straight line, sometimes it won't drive straight. What will actually happen is the motors can actually drift, causing the robot to swerve a little bit over time. And this is can be harmful because you can tell the robot to go straight and it can just swerve off path, making it a impractical cut, and it's not accurate. So how did I fix this? So remember that pitch I used to keep the left right? So basically, we keep that pitch at 0. We want to say, hey, keep that pitch at 0. If you go anything above like 20 degrees or anything above or below negative 20 degrees, bring it back to the 0. Try to keep it as 0 as possible so we go in that straight line. So here's evidence of this working. So to display it, we're actually using lights. So we have a green check mark here, showing that yes, we're in the correct safe zone. I'm moving it with my hand. I move it to the right a little bit. Nope, not in the safe zone. So we're gonna act upon that, move it straight again, and we're gonna go the other way, and boom, and there you go. It doesn't work. So we move it straight back again, and we get a check mark again. So here is our most important sensor, the ultrasonic sensor. So this is what it looks like. The hardware looks like. So you know how dolphins use echolocation to detect how far something away is? This is exactly what it does. It sends out an ultrasonic wave. It hits the object and comes back, and the time it takes for the object to come back, the distance, you can figure out the distance away. So I have it set to 30 centimeters, so around 1 foot. So if I'm about to crash into an object, I can detect that, and I can stop, reverse lawnmower, turn around, and go the other way. So this is all for crash and obstacle avoidance and crash prevention. So here's the code for this. As you can see here, you can pause the video if you want to look at the code more specifically. And here's the accelerometer. This is very similar to the accelerometer in your car, in the way that it detects how fast you're going. And this is just simply for data collection for more accurate results later down. So humidity, temperature, and air pressure. Here's another sensor. The humidity is right here, and the air pressure and temperature is right here. And it's exactly what it says. It measures the humidity, temperature, and air pressure. Why is this needed? So in the lawnmower, I want to see how hot it is, because it could actually overheat. The air pressure and the humidity is there to see for fun, I guess. It's kind of cool, because you can just detect your outside environment to see what the climate's like. We have our joystick, which is our used to push in and out, and this is what uses to start the program. So I'm going to push the joystick down. So we have a joystick right here. Here's a similar one. We have our up, down, left, right, and then we have our push down. Okay, so when we push the joystick down on the Raspberry Pi right here, this one, we're going to actually start our master program to say, hey, go cut the lawn and tell me when you're done. Okay, we push it again in case we need to stop it at any time. That's our fail safe. Okay, and finally, to program our motors. So this is a big thing. I actually did this in 3 different parts. The first time I ever did this was very hard, and I couldn't even get the motors to run, and I spent around 4 hours trying to do this. And this is where, after 4 hours of work, this is all I got. This 15 lines of code. All this did is here. I was programming the Raspberry Pi right here, of course, and here's the motor and motor controller. And what this did was, it made the motor spin. I didn't know what direction. I didn't know how fast it went. I didn't know anything. It was just made it spin. I didn't even know how to make it stop. So once I learned how to do that, I messed around with the values a little bit, the lows and highs. As you can see here, low, low, high, 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 low, low, high. And then the print duty cycle, 50, 25, 50, 75. So that all that does, it changes the speed. So we have low, low is both equal to stop. So low, consider that as 0, and high, consider that as 1. So we have high as 1 and low as 0. So that's going to make us move forward. Okay, and the opposite of that, of 1, 0, is 0, 1, and that's going to move backwards. And thus we have our low, high. And then we have our low speed right here for 25. And our medium speed, 50%, sorry, 25%, 50%, and 75%. And that finally led me to my basically final code. So it compiles all of the previous code in one master document, and I can you see here we have our part of our ultrasonic sensor here, and yeah, it compiles all of it in one big master program essentially. So what was the results of all of this? So we have our different lawnmower speeds. My lawnmower is actually double the speed of a standard lawnmower, and that gives like 5270 wheel RPM. It gives about 1.4 horsepower at 5.75 foot-pounds of torque. This helps me get out of holes easily. My lawnmower weighs 20 pounds compared to the 90-pound gas lawnmower, so it's easy to pick up, and it's very maneuverable in the hands. And sound. Lawnmowers can actually be dangerous in the sound because prolonged exposure is not good for hearing. So here we go. Our lawnmower is 50 decibels, which is underneath the 70 recommended, safe, max recommended decibel range. And then the standard gas-powered lawnmower is actually 95. So here's my original design, my prototype, and here's my final design. And I'd like to wrap it up and say that by lawnmowers like advanced artificial intelligence, which is through the integration of various sensors, and it allows it to have maximum precision and maximum safety, and it can take place of humans for a safer and cleaner cut, and with the custom 3D printed parts and everything. So yeah, my name is Josh Kakade. I created this smart mower, and thank you for listening.